If your goal is to use a Taylor polynomial to approximate your function, wouldn't it be kind of nice to know how far off you were to be able to calculate the error in your approximation? And that's what we've been doing with our calculator, but it's a little bit contrived. We'd have our calculator give us the exact value of, let's say, the square root of e, and then we would use our Taylor polynomial to approximate it, and then we could very easily subtract. But in a practical situation, that is not the case. So here we have our second objective, where we're going to be able to calculate the error of a Taylor polynomial using the Lagrange remainder. Lagrange was a mathematician. His name might look familiar to you because that's the guy who came up with the prime notation for derivatives, like y prime, y double prime, and so on. All right, so let's draw some conclusions from the first objective. Remember, we were initially finding Taylor polynomials for f of x is equal to e to the x, with our goal being to evaluate it at 0.5. In other words, e to the 0.5 or the square root of e. And our Taylor polynomials were centered at x is equal to 0. So truly, it was a Maclaurin polynomial, right? All right, so in our table here, this second row here is 0.5 plugged into each of these Taylor polynomials, the 0 degree, the first degree, the second, the third, and the fourth, and so on. And we're comparing that in the third row to the actual value of e to the 0.5 power, at least accurate to 3 decimal places. The last row there is the error, which is just the difference between these two things. How far off are we from the actual value? And just take a look. Seems very obvious that as we increase the degree of our Taylor polynomial, we get more and more accurate. Every single time we add an extra term to our Taylor polynomial, we're going to add a little bit more accuracy. We're going to take away from our error. So there's our first conclusion. The approximation becomes more accurate for higher degree polynomials. In the box here it says as n approaches infinity. As our degree of our Taylor polynomial increases, as it approaches infinity, then our Taylor polynomial is going to approach our actual function. And this is actually a goal for this whole entire module. We're beginning with Taylor polynomials, and we're going to end with, just why stop at the third degree or the fourth degree? Why don't you just keep on going forever? And that's what's called a Taylor series. Again, that's going to be the bookends of this whole entire module. All right, let's draw another conclusion here. Let's focus specifically on the fourth degree Taylor polynomial. So now we're plugging in different x values up here into our fourth degree Taylor polynomial. And starting with x is equal to 0, we would get 1 for our Taylor polynomial, our fourth degree, but we get 1 also for e to the x. There's no error there because that's where we were centered, right? Just like same thing happens with a tangent line approximation. You're exactly on that point of tangency. They're going to give you the same value. All right, now we're going to start moving to the right slowly. If I plug in 0.5, here's the value of the Taylor polynomial, and here is e to the 0.5 power, this time accurate to 4 decimal places, and the error calculated. Plugging in 1 into both our Taylor polynomial, and then here is just the value of e, of course, 4 decimal places in the error. Just take a look at what's happening to the error right here. As we move further and further away from our center point, and our center point was x equals 0, what's happening to your error? You can see that the error is increasing, right? It's getting bigger the further away that we were from our center point. Again, the same exact thing happens with a tangent line approximation. The further away you are from your point of tangency, the less accurate your tangent line is for the purposes of the approximation. All right, so what I've got here are both the e to the x function graphed together with the fourth degree Taylor polynomial. Can you see the difference between those two things? So the dark purple function, that's your e to the x, and then the magenta one there, the pink one, is the Taylor polynomial. It's really hard to see the difference between those, right? All right, so we're going to look at it slightly differently. We're going to subtract these two functions. I'm going to take f of x, which is our e to the x function, and we're going to subtract away our Taylor polynomial in order to get this graph right here. So this is what we got. And this is what is called the error function. It is the remainder that's left over after we subtract our two functions. So right here around the origin, it's perfect. It's perfect because it shares that point. Any Taylor polynomial is going to share its point that you center it at, right? And then as we move slowly to the right, you can see that the error is increasing. So at 2, the error is, it looks like it's pretty close to a half. At, this is about 2.5, the error is almost 1.5, and then so on. And the same thing happens as we move to the left. Again, the conclusion being that the approximation becomes less accurate the farther away that you move from your center point. So those are our two conclusions about our Taylor polynomial. The more degree, or the more terms that we've added to our Taylor polynomial, the higher the degree, the more accurate it's going to be. And the less accurate we're going to be the further that we move away from our center point. Okay, so we know that our Taylor polynomial is only an approximation for our function. They're not exactly the same. If they were exactly the same, you're not actually approximating anything. You're getting the exact value. So if we added a little something to the right-hand side of this, wouldn't they balance out? Could we add something to the right side of this to balance it out so that this approximation is no longer an approximation, it's actually equal to the original function f of x? And the answer is yes, we can. And that's called the remainder. The same thing happens whenever you do long division. You have a little bit left over. Well, if you add that little bit back to your quotient, you're back to your, whatever it is that you divided into your dividend. Okay, so we're going to define a function here, and it's going to be the remainder function, and it's going to start with what we just had. F of x is equal to our nth degree Taylor polynomial plus some sort of remainder function. I've got to add a little bit of extra in order to balance it back out to get to the original function. Now, in practical situations, you don't know what this remainder is. Our goal is to try to figure out what it could possibly be in order to figure out how far off our approximation is. So since that's our goal, let's solve that equation for the remainder function by just subtracting that Taylor polynomial to the other side. So in most situations, you're either over approximating or you're under approximating your actual function with your Taylor polynomial. And since we don't know which one it is, like it's going to be positive or negative, this remainder, we're just going to go ahead and take the absolute value of that thing. And taking the absolute value of it, that is what we're going to define as the error in our Taylor polynomial, how far off we are from the actual value with our approximation, okay? Again, that's called the error. It's just the absolute value of the difference between our actual function and our Taylor polynomial. Okay, so now what I'm going to do is I'm going to start taking some derivatives of this. Our goal is to try to zero in on this remainder right here, okay? So let's start taking some derivatives of this thing, like so. I'm just going to call this thing r for our remainder function is going to be equal to our function minus some sort of Taylor polynomial. Let's start taking derivatives. So I take the derivative of the left-hand side. It should be equal to the derivative of the right-hand side. And since this is just a difference, we have a difference rule for derivatives, which just basically says the derivative of a difference is the difference in the derivatives, right? Okay, so and you can continue this. So we can take the second derivative of this if we wanted to, second derivative, and so on, right? You can continue this. But since this is a polynomial, right here, there's a limit to the number of times you can take the derivative. Do you know what that limit is going to be? How far you can go until it's 0? Here, let's take a look. Let's do a little tiny investigation. Let's say y is equal to x. Very, very simple. Taylor approximation, tangent line probably. Take its first derivative, we just get 1. We take its second derivative, and we get 0. So we started with a first degree, and it took 2 derivatives before we got down to 0. Let's go again. Y equals x squared. You take its derivative, first derivative. It is 2x. Take its second derivative. You just get 2, its third derivative, and that's where we got 0. The second degree gives us a 0 derivative when we take 3 derivatives. So what would it be for x to the third, do you think? How many derivatives? 3 derivatives? 4 derivatives? 5 derivatives? The first derivative is 3x squared. Second, 6x. Third, 6. Fourth derivative, remember you write the fourth derivative like this, is equal to 0. So in general, if you have p to the nth power, whatever that is, well, p sub n, how many derivatives does it take before you get down to 0? It's going to take n plus 1 derivatives, right? When it was the first, it took 2. When it was the second, it took 3, and then so on. So over here on the left-hand side, I should be able to take n derivatives of this minus b. Whoops, oh, that became an r for some dumb reason. Okay, there we go. But as soon as I take the next one, then the polynomial disappears. Because that part's going to be 0, minus 0. And so this is what's going to help us zero in on that remainder, taking n plus 1 derivatives. It's kind of like the next term, right? We took n derivatives in order to get there. Well, what happens when we take the very next one? Well, the polynomial disappears, and all we have left is the derivative of our remainder function is exactly equal to the derivative of our function. Okay, all right then. So by construction, at x equals c, the nth derivative of f of x is equal to the nth derivative of the polynomial function, the nth degree Taylor polynomial. But if we take one more derivative of that Taylor polynomial, it's going to go to 0. So this is what we have. And we reestablished our absolute value, of course, because we want to make sure, hey, our error here is positive. We have the remainder function's nth derivative, the absolute value of that, should be exactly equal to the nth derivative of our function, the absolute value of that. All right, and that is what we're going to use to bound the error of our approximation. And like I said, you can think of it as the next term, the next neglected, or the first neglected term of your Taylor polynomial. The whole process of putting it together, you went to n, but what if you went to the very next one, the n plus 1th term, okay? So like I said, we're going to use that in the next video in order to bound the error in our Taylor polynomial.